Hello everyone, my name is Carlos González Rodríguez and I am going to present my work for the subject Deep Learning for Acoustic Signal Processing. Me and my teammates choose the topic Emotional Speech Recognition since it is a pushing trend in artificial intelligence technologies. We developed our project using a Kaggle database called RapDes. This dataset is composed by 1,440 audio files of distinct people, women and men, saying the same two test sentences but emphasizing different emotions: anger, happiness, sadness, calm, neutrality, surprise, fear, and disgust. Based on this data, we decided to address two different tasks: gender classification using machine learning and emotion classification using deep learning. After a little research on the internet, we found out that building different models for male data and female data was a good idea due to the pitch differences between the two genders. So we decided to develop a unique and fancy solution. It consisted of a first machine learning model for deriving the gender of the speaker, followed by two deep learning models for deriving the emotion present in the voice signal, one for males and other for females, as it can be seen in the image. We did all the work in a Google Colab notebook to take advantage of Google's GPU. First of all, we built a pandas DATAFRAME object for handling the data. The information about the emotion included in the voice signal, the gender of the speaker, and other unnecessary parameters for us were included in the name of the file. All the parameters followed a numerical code. For instance, in the gender column, females were identified with number 2 and males with number 1. Next, we performed a brief exploratory data analysis to check the appearance of the signals. At that moment, we detected that the useful data was surrounded by huge silent spaces, so we deleted them using the trim function provided by Librosa library. In this slide, you can see the result of that operation. Then we analyzed the signal in the spectral domain using the SPECTRAL function, also provided by Librosa. And we checked the distribution of the MFCC coefficients throughout the frequency bands. In both cases, it is noticeable the elevated presence of high-frequency features in female voices. Finally, we did some k-means clustering to see the suitability of splitting the data into two clearly different groups, and we obtained a promising result regarding the upcoming machine learning task. Before addressing any artificial intelligence algorithm, we created a config class just like we did in the classroom. We used this block of code to set once and for all every parameter involved with data extraction and processing. The sampling rate, the number of classes to classify, or the learning rate, among others, are specified there. At this moment, we moved into machine learning modeling. We used both temporal data and spectral data for doing gender classification, because we wanted to verify that it is better to use the second rather than the first. We followed the usual workflow. First, we split the data into two groups, 75% for training and the remaining 25% for testing. Then we created two config objects, one for raw data and other for frequential data, since we have to use MFCC coefficients in the second case. And we extracted the information using the prepare data function that we saw in the laboratory sessions. Finally, we labeled the expected outputs for the training process. We tried three machine learning models. The first was logistic regression. We built and trained it using the functions provided by scikit-learn. Then we tried support vector machine, like you can see in this slide. And finally, we tested random forest. In this slide, I will summarize the obtained results. As you may see in the table, spectral data worked way better than raw data. This is especially noticeable when looking at the testing set, where the raw data doesn't even make it to 60% accuracy. On the other hand, logistic regression proved to be the best method thanks to its 90% accuracy in the testing set for the spectral data. Next, we address the emotion classification task. To do this, we use a bidimensional convolutional network. This kind of models can perform very well if we put different MFCC bands as inputs. creating an image. The convolutional layers are used to extract the features from the data, while the fully connected layer does the classification job. In the right part of the slide, you can see the coding block, which was obtained using Keras algorithms. As I mentioned before, our idea was to train one model for male audio files and other for female audio files. In this slide, you can see the data preparation process. It was quite similar to the process we followed for the machine learning task, but this time we had 4 data sets for training and testing each gender's model. Besides, we used only one config object because we employed only spectral data once we proved its performance. And it is also noteworthy that we used the toCategorical function to create a one-hot encoded matrix for labeling the data used for starting the backpropagation operations, since we had to differentiate between 8 different classes. The obtained results weren't very good, as you can see in this slide. The loss was unacceptable at the end of the training processes, and the accuracy didn't even reach the 50% in both cases. The female model were particularly bad, with a 10% accuracy in the last epoch. To improve these first results, we decided to expand our initial database since 1,440 audio files were too few to address such a challenge. In this sense, we added the CREMA-D dataset, also available in Kaggle. This dataset was pretty similar to RAPDES, and it included more than 7,000 audio files with the same emotions except for surprise and calm. Then, we decided to keep both genders together. To split them ended up being an error, because we ran out of data for training. Finally, we created a new variable in the data frame called label to join the gender and the emotion in a single element, because we would no longer have 2 different models. This new variable had 16 possible values, and it can be seen in the last column at the right. Due to the decisions we made here, the initially proposed model couldn't be achieved, and the classification task would have to be done separately. This time, the obtained results are better. The loss is around 1.5, and the accuracy is about 50%. This is a valuable improve, especially considering that the accuracy for the female audio files was at 10% in the first attempt, and that we were classifying between 16 classes instead of 8. For the FREESOUND challenge, we decided to try and evaluate data augmentation methods in our emotion classification task. We used an algorithm called speed and pitch, which expands the time base of the audio signal and fills it with interpolated data. Then the time base is restored. This time, the training of the model took 8 hours, much more than before, due to extra data points generated. Unfortunately, the results didn't get too much better at the end of the training process, but at least the accuracy grew fast and the model quickly converged. Finally, we can extract some conclusions from our work. More investigation about different models and algorithms would probably lead us towards a more efficient and accurate model. It is really difficult to classify between 16 different classes. A powerful GPU is crucial for data learning development, and lots of applications for audio can be done using deep learning from data leveling to music creation. And this is all. Thank you for your attention.